Okay, so hello everybody, I'm Agostinelli, and today I will present you our work about large eddy simulation for the flame dynamics analysis in an aeronautical engine combustor. So this work has been done in collaboration with Davide Laera, Laurent Giquel, who is my thesis supervisor, Stéphane Richard, and Thierry Poinçon. So this is the outline of the presentation. First, I will present you the context and the research questions. Then I will focus on some results, and in particular on the impact of H2 enrichment on flame structure and combustion dynamics in the Pekinsta test bench. And I will focus on the effect of heat transfer and H2 addition. And finally, I will present you the conclusions with the future works and the dissemination. So as you all know, the framework of the project, there was, at least before the COVID-19, the growth of air transportation. This was leading to the problem of the impact on ecosystems, so with the need of implementing clean combustion technology and increase engines reliability. If we have a closer look to the projection of CO2 emissions from the aviation sector, you see that by 2050, we will have that the CO2 emission will be 3 times higher if compared to the current level. And even if we take into account the efficiency improvement due to the research and development, this is still not enough, especially if we consider the net zero target of the European Union. So we need to do something, and in particular, in recent years, a lot of lean combustor has been developed to do so. But as we all know, these lean combustor have some flame dynamics issue. For example, there are thermoacoustic instabilities, or lean blow-off, or again, ignition capabilities are not the best ones. So we have different solutions. For example, we can change geometry, and this has been done by Safran helicopter engines with the spinning combustor technology. So in practice, this new technology, which has been recently patented, has increased the lean blow-off and ignition capabilities. Or another option is to change fuel. So to add, for example, H2 hydrogen to our combustor in order to change, for example, the thermoacoustic behavior. So to stabilize, for example, some cases which are not stable. And this has been proposed, for example, recently by Safran or Airbus. My objective in this context is to assess the reliability of large eddy simulations, and in particular to answer the following questions. For example, we can ask if is less able to correctly predict the flame stabilization in this new configuration, so in this spinning combustion technology, for example. Or again, is the numerical modeling appropriate for hydrogen flames? For example, we saw that we need the complex transport properties to take into consideration B-fuel flames with hydrogen. Or again, what is the solution dependency from the mesh? So can we build a static mesh adaptation approach for reliable less in reacting flows? Also, for example, the heat transfer effect on less and the hydrogen addition. And finally, can we use LES as a design tool? So in this presentation, I will focus on this part, so on the heat transfer effect and hydrogen addition, which is the ongoing work at the moment. So to do that, we will focus on the Pekinsta test bench, which is a well-known test bench operated by the German Space Agency. And in particular, there are 2 burners, the atmospheric burner and the high-pressure burner. And both of them are being operated with different H2 enrichment to analyze the effect of H2 enrichment on the flame dynamics. For the sake of being short, we'll focus on the atmospheric burner results. So we selected 2 operating conditions. We started from an operating conditions, which is condition A, which is a stable operating condition from the thermoacoustic point of view. And in particular, we have no hydrogen in this case, so we have only methane flame, technically premixed. And we compare to the different operating conditions available in the literature, for example, Franzelli or Meyer et al. And so on. We are operating the test bench at lower power and higher equivalence ratio. So the idea is to validate our modeling approach with this stable case. And then we will pass to condition C, which is a condition in which we inject hydrogen. So we have 50% of hydrogen by volume with respect to CH4. And we analyze the effect of hydrogen enrichment on the flame structure and flame dynamics. And we see if we are able with less to analyze this and to reproduce this thermoacoustic behavior. This is a slide on the computational domain and boundary conditions. So, of course, we use the AVBP LES code with the sigma turbulent closure, TTGC, so third order scheme. The inlet and outlet boundary conditions are treated with the classical NSA-BC formulas, and the walls are treated as no slip with heat losses. This is the chemical scheme that we use. So we derived an ARC chemical scheme and we validated it in a PCI last year. So basically, we derived this scheme from the GRIMEC 3.0 mechanism. It comprises 20 transported species, and we validated it through some Cantera calculations of 1D premixed and diffusion flames. So you see here an example of the laminar flame speed calculation for different blendings of CH4 and H2 with air. The computational mesh is showed in this slide, and in particular, you can see on the left that the typical mesh resolution in the combustion zone is of around 300 micrometer. We performed also a solution sensitivity analysis to the mesh. So this has been accepted for publication on physics of fluids. So we applied an adaptive mesh refinement method. And for the combustion model, we used a TF-LES model with the Charlotte efficiency model with dynamics formulation, because sometimes we need the dynamic formulation of the beta parameter, as underlined, for example, by Volpiani et al. In 2017. This is especially true in the unstable case. So we pass now to the condition A, which is the stable condition. And we analyzed, in particular, in this case, the effect of thermal boundary conditions, which are very important in this test bench. So the problem is now how to set this thermal boundary condition. The fact is that there are not many experimental data about thermal boundary conditions. There are just some measurements of the fluid temperature made by Meyer in 2007. And based on this study, for example, Benard et al. In 2018 just set the temperature of the chamber walls by tuning this temperature. And for example, there are also other experimental data about the backplane and the bluff body, but in different operating conditions, so measured by Yin et al. In 2017. So what we have done, we have simulated these other two cases, and we have tuned our thermal resistances. However, if we do that, this approach takes into account the heat losses, but does not take into account the preheating of the gases. And also, we have a thermoacoustic instability of the flame, which is not experimentally observed. So you see here on the right the fast Fourier transfer of the recorded signal pressure in the combustion chamber. And on the left, you have the FFT of the LES signal. And you see that basically in LES, we have a thermoacoustic instability at around 300 Hertz. And here in the center, you have an animation of the thermoacoustic oscillation, in this case, in LES. So to solve this issue, we pass to LES heat transfer coupled simulation. So basically, we meshed also the solid part. So here, for example, we have a mesh of the solid part with 15 million cells. And we have at least 5 points in the thin regions, so in the chamber walls. And you see here in the slide, in red, you have the solid part, and in blue, you have the fluid part. Of course, we had to set also some thermal boundary conditions in this AVTP software, so in this code which solves for the conduction in the solid. And basically, there are different correlations to estimate the heat transfer coefficient on the external walls of the solid part. So in particular, if we guess the temperature of the walls, we can also estimate an equivalent heat transfer coefficient, which takes into account somehow also the radiation losses. If we do so if we pass to coupled simulation results, what happens is that we are able to recover, again, stable conditions. So for example, the corner circulation zone gets colder. We note a preheating of the gases as observed experimentally in 2007. And now we have a stable condition. So if we start from the condition that we had before, so in a stable condition, and we go a bit later, we see that now the flame does not oscillate anymore, and the case is stable again. We pass now to the effect of hydrogen enrichment. So now with the coupled simulation, we are able to recover the stability, the thermoacoustic behavior of the stable case. Let's see what we can do with the unstable case, with the hydrogen addition. Experimentally, it happens that as soon as we inject H2, the flame starts to oscillate at two frequencies, at 280 Hz and 470. And in particular, if we compute the acoustic modes with our ADSP Helmholtz solver, we have these two modes. So the first at 260 Hz is an Helmholtz mode, the plenum and the chamber oscillate in phase. And the second is a mode at 480 Hz, it's a chamber mode in this case. So we recover the two thermoacoustic oscillations that we have, that we notice experimentally. The question now is only LES able to capture these dynamics? The answer is not really, because as soon as we inject hydrogen, as you see in this transition animation, you see that the flame gets shorter and it starts to oscillate as it happens in the experiments. So we are able to see that the flame, the case becomes unstable. However, if we look at the FFT of the LES signal, we see that the flame oscillates at a frequency which is not the right one. So we oscillate at 290 Hz, which is much closer to the first mode, so to the Helmholtz mode. But the flame does not respond to the chamber mode. And here you see a comparison between the OH-PLIF experiments. Here you see that the flame, there is an evident flame roll-up here at a certain point of the cycle. Then the two branches get closer, and then they separate again. And in the LES, we have almost the same dynamics, I would say. So we have some flame roll-up here, and then the two flame branches get closer. However, as you can see, the flame is longer in LES. And also, when the flame is downstream, it detaches from the bluff body. This is something that we do not notice in the experiments. So the good news is that with only LES, we are not able to couple with the combustion chamber mode at 470 Hz. With coupled simulation, so with LES heat transfer coupled simulation, we are able to capture the flame dynamics, and now we are able to couple with the combustion chamber mode at 500 Hz. However, you see there is a small peak here around 280 Hz, but it's not really comparable with the one seen in the experiments. And this is due to the preheating of the gases now that we are able to capture with the coupled simulation. So you see that there is a strong preheating here. You see also the temperature of the solid part of the coupled simulations. So to conclude, we analyzed the effect of heat transfer and H2 enrichment in the pre-Kingston burner, in particular in condition A, which is a stable condition. We trigger an instability if heat transfer is not correctly taken into account, in particular when the corner recirculation zone is warm. In the condition C, the flame gets shorter with ignited branches in the corner recirculation zone, and the case becomes unstable, as in the experiments. But in LES, in order to capture correctly the dynamics of the flame, we need to use LES heat transfer coupled simulation and also a dynamic formulation of the efficiency model. As future works, we plan to perform DMD analysis on the experimental data in LES in order to understand which parts of the flame respond to the acoustic modes. And also, we are performing an analysis on the pressure effect of H2 enrichment in the high pressure pre-Kingston burner. So a list of the publications that we made. First publication at the ASME TurboX last year about the spinning combustion technology. And as I said, a physical fluid paper on the static mesh adaptation method, and also something about the stabilization mechanism of CH4 premixed swilled flame enriched with an open mixed hydrogen injection for the PCI of last year. And we plan to do some other work on the things that I've shown you today. So this work has been made possible thanks to the collaboration between Safran, Surfax, and TNU, which is a member of the Anulite project, and that is operating the spinning combustion technology chamber, and the German Aerospace Center. So thank you for your attention, and if you have any questions, I will be happy to answer.
Okay, thank you, Walter.